Hi guys, welcome back. Sorry if the linear functions were a little bit of a disaster. To be fair, when I think about SAT, there are a lot of linear equation type things on there. But I think they will be the easier ones. Like generally, they're just going to ask you to either write the equation or solve the equation. And I think those are pretty straightforward, especially if you feel confident enough to write the equation. I feel like once you have the equation written down, the solving part is a little bit easier. So this week, we're going to look at quadratics and polynomials, which are one step above or like one level higher than linear. And these are a little bit more rare to be on the SAT, but they would probably be, I would say, the second most common thing that you will come across. A lot of the stuff is linear, and then there's just a bunch of other random things in there, but this is the other biggie. Okay. So let's first take a look at quadratics. And again, the Google Slide document that is attached to this is what I'm using these examples from, and I'm going to write some things down. You guys can do that with me or not. It's really up to you. Alrighty, so when we're talking about a quadratic, I'm a very visual person. A quadratic graphically is a parabola. So, if you're looking at little XY axis going on. It could be a cute little pointing up parabola, little U shape. Might be a cute little pointing down parabola, U shape. But it's always a parabola. It has a line of symmetry that can cut the parabola in half equally, straight up and down. Some other defining factor about parabolas is this low point here is called a vertex or a minimum because it's kind of the lowest spot on this graph. On this parabola here, though, since it's pointing down, the vertex is considered a maximum because it's the highest point on the graph. And truly, when you're talking about the minimum and the maximum, you're talking about the y values at those spots because how high or how low is how does y go? Oh my God, I could talk about this forever. I'm getting so excited. I need to stay focused. So when you're considering a quadratic, it can be written in different forms, much like a linear equation. So linear, we had slope intercept, point slope, and standard. Quadratic has three forms as well. Standard form of a quadratic is something like y equals ax squared plus bx plus c. Now, when you're in standard form, it's not super helpful. Just by looking at it, the only thing you can tell about the graph is that C is your y-intercept. But if I needed to find the vertex or wanted to find the vertex, there's a little formula for doing it. It's negative b over 2a. So, and then you have to plug that value in to find out what the y value of your vertex is. Also, fun fact, the x value of your vertex is that axis of symmetry that I talked about, that vertical line that cuts your parabola equally in half. And guys, the vertex is pretty important to find if you're in standard form. If you want to go graph it, also it's like the halfway point. So if you have that, that's a good place to start from. And then you can pick x values on either side to plug in to your equation. So, if you found that this vertex happened to be at -2, -3, then I might pick -1 to plug in, and then I can plot my graph a little better, and -3 to plug in and all that stuff, okay? Standard form's not great, I'm not gonna lie. Another form that you can write a quadratic in is vertex form. So vertex form looks like a parenthesis x minus h squared plus k. And vertex form is really good. It's maybe my favorite. I don't know. If vertex and intercept were having a fight, and I don't know, I feel like I'd be happy if either one won. They both are awesome. Vertex form is really good because right off the bat, h and k that's my vertex. I don't need to do a little formula to figure out where the vertex is. They're just staring right at me, okay? So like I need to be able to differentiate between the forms, because if I'm looking at something like this that has an x squared and an x and no parentheses, I know that that's in standard form, versus something like this that has parentheses squared, that's in vertex form. I need to know the difference so that I know what the numbers are telling me. So if you see something like this, parentheses squared, the number inside the parentheses but opposite is the x value of your vertex, and the number outside being added or subtracted is the y value of the vertex. Now, just like with the other one, the x value is your axis of symmetry. Sorry, I gotta be a little funny. The a value here is kind of like slope. I always call it slope-ish. And the reason I call it slope-ish is because like parabolas don't have slope. They're not traveling up equally on either side, but it will do this a value slope one time from the vertex. So like if I know that, again, this vertex here is maybe at -2, -3 again, if the slope here, or the a value, is 2, I could go up 2 over 1 in either direction to kind of get an idea of what my parabola looks like. So that's nice. Vertex form. We love it. Intercept form, though, we probably love equally as well, if not more sometimes. So intercept form, or sometimes called factored form, looks like y equals a, parenthesis, x minus r1, parenthesis, x minus r2. And maybe this is ringing some bells, especially when I called it factored form, because factored form, again, is like really a good form to be in for a lot of reasons. A right here is kind of that slope-ish thing again. But before I can do anything with slope, I really need to have that vertex. And unfortunately, again, in intercept form, you don't have your vertex. The R1, R2 values, these are your x-intercepts. Intercepts, oh my God, spelling. And notice that in here they're negative, and when I took them out, they're positive. So they are opposite of what you see. Like if you see x minus 2 and x plus 3, then my x-intercepts are 2 and -3. Okay, so the opposite of what you see. So you can like go plot those points. Now, the really nice thing about having your x-intercepts is like you have 2 points, but also it's symmetric. So again, like maybe a better example here, let's say that this x-intercept is at 0 and this one was at -4. I could just boop, 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 count into the middle, and -2 would be right in the middle. And so that would be your axis of symmetry. So we can kind of, to find a middle, we add the 2 roots and take half, and that will give you your axis of symmetry, which again, kind of working backwards here, if I know my axis of symmetry, I know the x value of my vertex, and I can plug it in to the equation and find the y value. Now, another big thing about quadratics, you can take any of these forms and rewrite it in any of the other forms, but I always recommend that you try to keep it in the form that they give to you, because if I have to change forms, that's wasting time. And again, time is everything when we're taking the math portion of the SAT. So when we're solving quadratics, focusing a little bit more on that, focus, Madura, come on. This was more graphically stuff. If I'm solving them, again, depending on the form, I'm going to solve it different ways, but kind of the best way and the fastest way to solve it. So like your number one goal is to try to solve by factoring. Now I say solve by factoring. If your equation is already in factored form, you're done. And so that's where we just set each parenthesis equal to 0. And you get your x-intercepts, and that's solving. So solving quadratics just means like low-key find the x-intercepts. Oh my gosh, I forgot to tell you why they call them r. They're roots. They like to call them roots. I don't know. Must have to do with the square root. So solve by factoring is kind of your go-to. So if it's not already in factored form, The best you can kind of hope for after that is it's in standard form, because you can't factor something that's in vertex form. You would have to take the vertex form, put it into standard form, and then factor it. So a good example of that really quickly could be something like y equals x squared plus 5x plus 6. This is not in factored form, it's in standard form. And so the way that we factor is, I always taught my students, I put a little x and I think about whatever multiplies to the last number and adds to the middle number. It's like a little game, whatever multiplies to that last number, that c value. But at the same time, those same two numbers have to add up to that b value. So here it's 3 and 2. I take the x and I split it equally, so x plus 3, x plus 2. And then you just set each one equal to 0, so, or they're just the opposites, as x would be -3 and also -2. Now, if you don't want to change forms, like probably the next best way to do it is to use a quadratic formula. I mean, I say it's the next best way, but it's not fun. But yeah, you can use the quadratic formula, which, if I'm remembering correctly, I feel like is something that they will give to you. Like, it's not something you have to memorize, but gosh, if you don't have it memorized by now, where have you been? It's x equals -b plus or minus the square root of b squared minus 4ac all over 2a. I didn't mean to throw shade there. I'm not good at memorizing. The only reason I have that memorized is because I literally teach it every year like 20 times. You don't, so it's okay. There are other ways to solve quadratics. Like, you could look at the graph, and when we're solving, we're finding the x-intercepts, so just see where they cross. If you're in vertex form, it's really just about getting x alone. So like, I'd subtract the k, or whatever that number is, divide by that, square root it, and then get rid of h. So I think that's kind of easy. When you're graphing quadratics, I kind of talked about that up here, but really you kind of always want to know the vertex. Vertex is the most important. Point. Because that's where everything's happening. Like, they're all meeting at this vertex spot here that is dividing this graph equally in half. So if I know where that halfway point is, and then I can get at least one point on the other side, I can just flip it over, boop it on the other side. So, you know, if you're in standard form, you got to do a cute little formula to get it. If you're in vertex form, you already got it. And if you're in intercept form, you got a lot of work to do to get it, because you have to get those x-intercepts and then count to the middle. And that's part of the vertex, but then I got to plug it back in. Now, if you're just trying to get a quick sketch, which is sometimes all you need, knowing where the vertex is and then what the a value is also helpful. So first vertex, second the a value will tell you which way the parabola points. If it's positive, it's pointing up. If it's negative, it's pointing down. If you have to write equations, again, it's really going to be dependent on just understanding these different forms. If they've given you the vertex, then you probably want to put it in vertex form, because you just bop them in there. If they've given you the x-intercepts, then you probably just want to put it in factored form. They're probably never going to give you A, B, and C, truly. So typically I can think, you know, they're going to tell you something like the x-intercepts, but then they want it in standard form. I can't see a situation, I can't think of a situation, and I've looked at a lot of SAT tests where they have you like rewriting equations. Sometimes if you're looking at the graph, they'll be like, write the equation of this. But I mean, you're just going to be looking at those x-intercepts. And if they don't have it in factored form as one of the options, then you just want to FOIL it out and make it look like standard form. And that's usually what I notice. So maybe we'll make that little note there. Writing equations. To change factored to standard, which I do notice a lot of, that's where you do that FOIL stuff. So for example, if I had x minus 7 and then 2x plus 1, everybody always teaches FOIL, but I don't know. I never knew what it meant. It's burst out last. But I always just think I have to make sure that each of these numbers here get multiplied to each of those numbers there. So I have to do the x with the 2x and the x with the 1. So 2x squared and then 1x. Then I got to do the negative 7 with each of the numbers over there. So negative 7 times 2 is negative 14x, and then minus 7. We combine some like terms for 2x squared minus 13x minus 7, and oh my goodness, we could factor it like I was doing up here and get all the way back to that. So like factoring and foiling undo each other. They are opposites of each other. Oh my God, let's talk about a polynomial. Eee! They're so fun. So a polynomial is just a higher level quadratic. So a quadratic always has something to the second power, x to the second power. There are two x's. A polynomial is going to be bigger than that. I mean, truly a quadratic is a polynomial, but a polynomial could be to the third or to the fourth or to the fifth or to the sixth or to whatever I want. So a polynomial is a many-termed function, i.e., like kind of the best way to show it is just with an example. And generally the way we write polynomials is y equals a times x to the n power plus b times x to the n minus 1 power. Don't freak out, I'll explain what I'm doing in just a second. Plus c times x to the n minus 2 power, as far as I need to go, all the way down to z, where I have no more x's. So the a, b, c, those like letters in front of the x's, those are just coefficients. You know, like when you see it, it might have a 1 here, a 2 here, like those are just going to be numbers. X is my variable, as always. This power stuff that I'm doing is just saying, this is the biggest one. And then we just want to count them down. So if I'm writing out a polynomial that has the biggest power of x to the 6th, then I want to start with that one and then put them in reducing order. So I'd have like x to the 6th, then x to the 5th, then to the 4th, then to the 3rd, to the 2nd, to the 1st, to the none. If any of them are missing, that's fine. You just don't write them, but you always want to put it in descending order that way, okay? I friggin' love graphing polynomials, but there is kind of a lot that goes into it. So really your best bet, or your like hope upon hopes, is that they give it to you in factored form. So just like we were talking about over here, factored form is going to show you your x-intercepts. But there's another thing to consider now. So here, when I was in factored form, this was raised to a power of 1. We didn't really see it, but if your parentheses or your factor is raised to a power of 1, or something that I don't see, then that x-intercept will have a line crossing right through it. If I have something in factored form that has an exponent of 2, or 4, or 6, or any even number for that matter, at that x-intercept, the polynomial isn't going to cross right through it. It's going to bounce right off it. Or sometimes we call that a turn. Oh my God, it does like a little mini vertex. Ah, you'll see what I mean. I'm excited. You might not be excited yet. You're going to get there. If I see parentheses and then it has a power of 3 or 5 or 7 or any odd number other than 1, because 1 crosses, then that x-intercept does a wiggle through it. And you might think I'm being cute, but the math term is does a wiggle through it. Okay? So for example, if I had some x-intercepts at -3 and maybe -1 and maybe 2, if the -3 had a power of 1, it crosses right through that spot. So it's just crossing through it. If it had a power of 2 or 4 or 6 or anything even at the -1 spot, then it bounces off of it. So boop, boop, it does a little bounce, or it does a little turn, or it does a little parabola right on it. It's so cute. If I'm looking at an x-intercept of 2 and it has an exponent of 3 or 5 or 7 or any odd number, then it does a wiggle through it, which kind of is this weird little flattening out thing, like that. And furthermore, like as I was drawing that polynomial, I realized there's another thing that we have to consider as well, and that's the way that the polynomial is pointing. So this polynomial happens to be pointing down and down. So another big thing to consider when I'm graphing polynomials is this thing called end behavior. And end behavior is great, kind of. So with end behavior, there are two questions you need to ask yourself. Is the polynomial even or odd? And all I mean by that is overall, is the highest power an even number or an odd number? So if I'm in standard form like this, I'm just going to look at the biggest one. And if it's to the 6th, it's even. And if it's to the 7th, it's odd. But if you're all in factored form like this, you got to add up each exponent, even the ones that you don't see because they're ones. And if you add up each exponent and you get 6, then you're even. Or if you get 7, you're odd. If it's even, then the ends both go in the same direction, either both down or both up. And if they're odd, they go in opposite directions. So like it starts down and ends up, or starts up and ends down. So the way to tell, so after I know if it's even or odd, like, okay, I'm even, to pick the right one here, the next question is the leading coefficient positive or negative? So maybe I'm going to get a little color in here. If you are even and positive, then you're up. If you're odd and positive, you're like a going up line. So it starts down, ends up. That's like going up line. If you are even and negative, you're pointing down. And if you're odd and negative, then you're like a going down line. And you can kind of see that here too. Like a quadratic is even because it's to the 2nd power. If it's positive, it's pointing up. If it's negative, it's pointing down. So I always just relate it back to the easy ones. Quadratics are even. Is it more like a quadratic or more like is it a positive quadratic or a negative quadratic? And like 2, 4, 6, 8, those are all quadratic-y type things. Odd is like a line, like we did last week. So linear equations go in opposite directions, like this, okay? And is it like a going up line or a going down line? So positive would be a going up line, negative would be a going down line. Graphing is so fun. I love it. But another big part of polynomials is how we solve them. And so if you're in factored form, you're kind of already solved because, again, when we're solving, we are finding the x-intercepts. But if you're not already in factored form, you could factor. So we could try to factor. Now, the thing is, you can only factor if you have 2 terms, 3 terms, or 4 terms. Just like 2 numbers or 3 numbers or 4 numbers. If you have any more than that, you can't do that. So a 2-term thing that I could factor might be something like 4x squared minus 9. Because they're perfect squares, you just get 2x minus 3, 2x plus 3. Ooh, or there's the cubic one. So another two-term thing is if you have something like x to the third minus 27. So when we had, so these are like perfect squares, and so you just square root to get each one. That's something that we did with quadratics. But when they are perfect cubes, you do it a little differently. You take the cube root of each one to get the first set of parentheses. So like x times x times x is x to the third. And 3 times 3 times 3 is 27. And then to get your next set of parentheses, it's actually going to be three numbers always when it's a cubic. You square the first number that you got here, multiply the two together, and then square the last one. And then your signs always go same, different, positive. So the same as what I started with, different than that, positive. Maybe one more like that. Another perfect cube type thing is if I had 8x to the third plus, that's a bad example, 125. These are both perfect cubes because 2 times 2 times 2 is 8, and 5 times 5 times 5 is 125. And it doesn't matter if it's a plus or a minus. Like with perfect squares, it always has to be a minus, but with perfect cubes, it can be whatever. So that first set of parentheses is always going to be two numbers. It's the cube roots of each of these. So we said 2x and 5. To get that second set, it'll always be three numbers. You take the first number and square it. So 4x squared. Then you multiply the two, so 10x. And then you square the last one, so 25. Signs go same, different, positive. So the same as what I started with, different than that, positive. Now the thing is, oh my goodness, we factored them, but we didn't even solve them. But they're pretty easy. Like this one, when I set it equal to 0, it'll be 3 over 2 and negative 3 over 2. With this one here, that would be 3, but now this is a quadratic that I should have mentioned doesn't factor, so I'd have to use the quadratic formula. And same thing down here, like I can solve this one and I'd get negative 5 over 2. And this over here is a quadratic, and with these cubics, they never factor, so you'd always have to use a quadratic formula there. Now, some three-term things, though, can factor, like we did on this one. So it's just with these perfect cubes that they don't factor. So another three-termed thing that we could factor is something like, let me make up a fun one, 4x to the fourth. Plus 12x, squared, plus 5. I was trying to think of a good number. I'm making this up off the top of my head. Flex. Okay, so if there are three terms, generally we just factor like I said over here. You look at that last number and think what multiplies to 6 and adds to 5. However, if there's a number in front, I like to do this sneaky thing where I slide it over and I multiply it. So now I'm really thinking, what multiplies to 20 and adds to 12? Multiplies 20, adds to 12. I think that's 2 and 10. We'll multiply to a 20. We'll add to a 12. And so then I write down plus 2 because it was positive and plus 10 because it was positive. And then we always split our x equally here. So here I just put 1 and 1 because like when you split 2 equally, that's 1 and 1. But here there are 4, so you got to put 2 and 2. And that sneaky thing that we did at the start, that multiplying the 4 over, I can't just not undo that. So like I did it, now I got to undo it. So I multiplied by 4, I got to divide each of these by 4. And so when I divide by 4 here, I can reduce and here. So we'll have x squared plus 1 over 2, and then x squared plus 5 over 2. And it's not really mathematically appropriate to keep fractions in factored form. And so those bottom numbers, they just pop up. It feels so illegal, but so fun. So you just move those Bottom numbers up. I like to call it slide, divide, bottoms up. So we'll have 2x squared plus 1, and then 2x squared plus 5. And again, at that point, these are both quadratics that don't factor anymore. And I know because they're two-termed quadratics, and with a two-term thing that is squared, it has to have subtraction in between, and these surely do not. So I would have to do something like the quadratic formula to figure out what x is there. And then the last thing that I kind of don't have room for right here is how I factor a four-termed thing. So an example of that could be, excuse me, if I have x squared plus, oh my gosh, x to the third, I lie, plus 5x squared minus 2x minus 10. If you have a four-termed thing like that, there's a couple of different ways I've seen it taught. Like you can factor by grouping, and that's super cute and pretty fun. I like to put it in a box. So each of these numbers go in a square on their own. So we got x to the third, 5x squared, negative 2x, negative 10. And then you just like factor out each line, like undistribute what the boxes have in common. So like this row here, I like to call it rows and columns. This row here has x squared in common. This row here has a negative 2 in common. This column here has an x in common. And this column here has a 5 in common. Now the thing is, once I pull out all the numbers, if I multiply back, I should get exactly what I have. Like x squared times x is x to the third. 5 times x squared is 5x squared. X times negative 2 is negative 2x. And then 5 times negative 2 is negative 10. So it all works back out. The numbers on the outsides are your factored form answers. So x plus 5 because it's positive. Smushed up against x squared minus 2. Which right here, I can see my answer, it'll be negative 5 because we're linear, so we're done. But right here, this is quadratic with two terms, but they're not perfect squares, so I can't factor it. I'd have to do something like the quadratic formula. Oh my word, that was long. So I'm going to stop this video here, and then I'm going to do some of these examples with you in the next one.